Hello and welcome back to Algorithms and Uncertainty. Today we will be considering another online problem, a very classical one, namely online bipartite matching. For this we will see a very simple deterministic greedy algorithm, which is optimal in terms of the competitive ratio it achieves, but then we'll see that with a slight twist we can turn it into a randomized algorithm, which is even better than this. What I find interesting about this entire problem is that this is actually a very old problem. People have studied this for a very long time, even before even these definitions of competitive analysis were introduced at all. So how do we define this problem? So we have a bipartite graph which we call G, and the vertex set, as usual, is a union of left and right, where there are no edges within L or within R. And a subset of the edges is a matching if each vertex, so no matter whether it is on the left or the right hand side, is included in at most one edge in the matching. So how should we think about this? Well, we have our vertex set L and our vertex set R, and out of these edges we now have to choose a subset so that every vertex is incident to at most one edge. So we couldn't, for example, add this edge because, well, this vertex is still free, but this isn't. This is a very simple offline problem. You can solve it, for example, by finding a maximum flow in this in an auxiliary graph where you add like a source and a sink, and then you try to maximize your flow from this source to the sink. And how do we turn this into an online problem? Well, what we now do is we assume that one side of the graph we already know in advance, and the other side now arrives online, one vertex after the other. When a vertex arrives, we get to know what edges it has, so which edges it has to which of the vertices on the other side. And then immediately and irrevocably we have to decide whether to match this vertex and how to match it. So we say that L is known in advance, and in each step one R in R is revealed including its incident edges, and then we have to immediately and irrevocably decide if R is matched and how. And our objective is to match as many vertices as possible. Which means nothing but to maximize the cardinality of our matching. And what is it that we're aiming for here? We are aiming for a strictly alpha competitive algorithm. So an algorithm is strictly alpha competitive if the expected value that we're achieving, we now have a maximization problem. This is why the inequalities now flip. The expected value that we're achieving is at least an alpha fraction of the optimal offline solution, and this should hold for any sequence sigma. So what can this look like? Let's see a very simple example which also gives us already an impossibility result for deterministic algorithms, namely beforehand we know only this is what the left-hand side vertices will look like. Now the vertices in R arrive one after the other. And let's say, okay, this is the first vertex to arrive, and we now get to see which edges it has. Now we have to decide, do we want to match this right-hand side vertex, or do we want to leave it unmatched? There's actually no point in leaving a vertex unmatched, but how do we want to match this? Well, let's say we use this edge. Well, if now this vertex arrives, then we are unlucky, because in this case what would have been the optimal offline solution would have been these horizontal edges, whereas our algorithm only chose this diagonal edge. So in this case we would have that the algorithm solution is only 1, whereas the offline optimum is 2, and you can see the same thing happening if we choose the other vertex. Let's also convince ourselves of this. So let's first assume that we don't know this vertex 2. Now let's say, okay, we'll do the opposite and we'll match 1 to A. But in this case, what could also happen is that this is our final graph. And now also vertex 2 cannot be matched anymore because vertex A has already been taken. Also in this case, what our algorithm got was only one edge, as opposed to what the optimal offline solution could do would be to take 2 edges. The first thing that we'll now do is to see, okay, actually we cannot do much, or we will not do any worse than what is happening here by analyzing a very simple greedy algorithm. This feels almost like a simple exercise, but the reason why we're doing this is because we're introducing a general framework to then afterwards analyze a slight twist of the greedy algorithm, which is randomized. Because what you can see already in this example is that randomization might pay off. So if here we match this first vertex A with vertex 1 with probability 1/2 to A and with probability 1/2 to B, then everything would be perfect, or not perfect, but this bad case would happen only with probability 1/2, and with probability 1/2 we would even get the optimal offline solution. And this is exactly what we are then trying to do with our online algorithm later on. But before that, let's come to the very simple greedy algorithm. I'd now like to consider a very simple greedy approach to the online bipartite matching problem, namely, whenever an online vertex arrives and we can match it, do match it. But actually the devil is here in the details, because we have to clarify how do we match the newly arrived vertex, because there might be multiple options of how we match it. How do we want to match it? Well, let's first consider the following algorithm. We index L, so the offline vertices, arbitrarily from 1 to cardinality of L. And whenever an online vertex R arrives, if there is an unmatched neighbor in L, we match R to the unmatched neighbor of smallest index. Good. So how does the tie breaking here work? Well, we just have this arbitrary indexing. Let's say we just draw our vertices in L from top to bottom somehow. So we'll have here A, B, C, and so on. And now this vertex, say 1, arrives and might have these edges. Then which of the edges will we be taking? Of course, we will be taking this edge. Now this vertex 2 might arrive, and let's say have this and this edge. Now what's the unmatched neighbor of smallest index? The neighbor of smallest index would be A, but it is matched. B is no neighbor, so we'll match it to C. Good. Now let's prove a very simple theorem, namely that greedy is strictly a half competitive. How could we argue that this algorithm is actually a half competitive? What does this mean? This means that from the optimal offline solution, our solution includes at least half as many edges as the optimal offline solution. And how would you want to prove such a thing? Well, the thing is that each edge from the optimal offline solution will have at least one endpoint which is matched in our solution. So of course here we even chose an optimal offline solution, but maybe let's go back to this example. Here, also regardless of what we're looking at, every vertex which is matched in the optimal offline solution, or no, every edge that is included in the optimal offline solution, which would be the horizontal edges here, for example, each of them has at least one endpoint which is being matched in the greedy matching. Because if both endpoints were unmatched, this means that the greedy algorithm did not choose this edge. And this is exactly the reason why we have this a half competitive ratio. But let's be a little more precise now, and let's go a little more into details on how we prove this, because this is also the proof technique that we will be applying later on for our more complicated algorithm and analysis. Namely, what we'll do is we'll actually use a proof technique which is more or less LP duality, but we don't actually need LP duality. We don't actually explicitly reference LP duality here. Namely, what do we do? Let's consider any offline vertex L, online vertex R. And now we'll set alpha L to be 1 if L is matched in AaU and 0 otherwise. Analogously, we'll set beta R to 1 if R is matched in AaU and 0 otherwise. Now, what is the sum of all these alphas and betas? Well, every edge that we have in our optimal offline solution appears actually twice in these sums. Namely, it appears once here by the left endpoint, and it appears once here in terms of the right endpoint. So this will be exactly 2 times the cardinality of AaU. And what we now claim is that the sum of these alpha L plus the sum of these beta R is at least also the cardinality of opt. If you now combine this inequality with this equation, then you'll see, okay, AaU will have to be at least a half times opt. And how do we show this second part? Well, consider any edge in our graph. And what do we now have? We have that alpha L plus beta R will have to be at least 1. Why that? Because otherwise, neither L nor R are matched, which means that L is still free when R arrives. But the algorithm didn't choose R, didn't match R at all. So we're getting to a contradiction with the greedy property, namely that every online vertex that can be matched will always be matched. And now what do we have? Well, what about the cardinality of opt? This is clearly no more than take the sum over all edges that are in opt, alpha L plus beta R. Just by this inequality, we can now write opt as at most this sum of these alpha L and beta R. Now, how often does one L or R appear in this sum? Well, it appears at most once, because every edge is at most, every vertex is matched at most once. So here, for this second inequality, we use that any L and R are matched at most once by opt. And where are we now? We now see that indeed this inequality is fulfilled, that the sum of the alpha L plus beta R is at least opt, if you read this here from the right to the left. And this already concludes the proof. So how does the analysis now work? Well, the way I'd like to think about this is we have some bank account. And while we're now running our algorithm, for every match that we make, for every edge that we add to our solution, we put 2 units of money into our bank account. Then, what's the final balance of our bank account after we've put the money in? Well, it is exactly 2 times the number of edges that we chose. And now, what we'll do is we'll compare this to the optimal offline solution. And what we are allowed is to take out 1 unit of money for every edge in the optimal offline solution. And this is exactly what we're doing here. Namely, we now don't only have our bank account, but we've also assigned the different units of money to the different vertices in our graph by exactly this scheme. And now this charging argument tells us that if we now take the optimal offline solution, then we can pay for this optimal offline solution by what is inside our bank account. And how do we do this? Well, for every edge inside the optimal offline solution, take whatever money we put on the both endpoints. There we will in total find at least 1 unit of money. Here this is actually pretty simple because we can say, okay, one of the endpoints will be matched, but what is actually only important here, and this is the way we will be thinking about this later. There is just enough money on the left and on the right endpoint. If we add this together, if we add this up, then we'll get at least 1 unit of money. And this means that the money we put into our bank account is enough to pay for the optimal offline solution. Okay, we put twice as much money into the optimal offline solution as we got, as the number of edges that we got. This is where the factor of 1/2 is coming from. Good. What we'd like to do now, and this is actually the main result of today's lecture, is we will introduce some randomization. And by introducing randomization, we can actually improve the algorithm and, or more precisely, we can improve the analysis, and we can improve this factor a half to 1 minus 1 over e, which is about 0.63. Now we want to introduce randomness to our algorithm and this way improve the competitive ratio. I've once again copied to you the definition of the greedy algorithm. There we index the offline vertices arbitrarily, and then whenever an online vertex arrives, we match it to the unmatched neighbor of smallest index. And the only thing that we now do is actually we change this indexing, and instead of saying, okay, take an arbitrary indexing, we say take a random indexing. And what do I mean by this? I mean we draw one of the cardinality of L factorial permutations uniformly at random. And then this algorithm will be called ranking. Why ranking? Because it introduces these L factorial, or draws one of the L factorial permutations, so it ranks the offline vertices appropriately. And what we will now show is the following. We will show that this algorithm is strictly 1 minus 1 over e competitive. Well, you should know that 1 minus 1 over e, this is like 0.63, which you can compare to a half, which is like 0.5, so we certainly gained something here. I should say that I never take these numbers too seriously, so whether this is now 0.63 or 0.5, these numbers don't have a very big meaning to me, but what is crucial to me is that this is actually the best competitive ratio that you can obtain for any randomized algorithm. So there is no algorithm which is better than 1 minus 1 over e competitive, or strictly 1 minus 1 over e competitive, not even any other randomized algorithm. For deterministic algorithms, you can even show that no algorithm is better than a half competitive. But as we see, randomization helps. Randomization actually breaks this barrier of a half, and we get to something that is at least somewhat better. Okay, what we now hope is that somehow by drawing this random permutation of the offline vertices, we somehow avoid these bad cases in which we were making an unfortunate decision by this greedy choice, namely that somehow it now happens that we are not always making the bad decision to this one offline vertex, which will exactly be used in the following step, or which will actually be necessary in the following step. Before we prove this, let's first make some important observation, which we will be using later when we're going through the proof. But now let's do this just before that. so that we can easily refer to this later on. Namely, what we'll do is the following. Let's show the following lemma. It actually has nothing to do with the ranking by itself. We could have also shown this for the greedy algorithm before. Namely, we fix now any order of the online vertices and one of the offline vertices and one particular offline vertex. For each round T, we now let UT be the set of unmatched offline vertices. When we're running the algorithm, on the graph G, and we let UT prime be the set of unmatched offline vertices on the following graph, take the graph G and remove all of L. So this means that we remove L and all incident edges from G. And now what we claim is that we have UT is a superset of UT prime for all T. So as I was saying, this has nothing to do with the random order so far. This is just some property that comes directly out of this greedy approach that we always match a vertex to an online vertex to the offline vertex of smallest index. And what is it that we claim here? What is it that we compare? On the one hand, take the execution of the algorithm on the full graph, the graph that is actually our input. Now change the graph, change it the following way, remove one of the offline vertices. This, of course, will change the matching somehow, the resulting matching. But what we claim is that the set of unmatched vertices, or unmatched offline vertices, when the vertex L is included, is only a superset of the set of unmatched offline vertices that we have if the vertex L is not included. And what will this be helpful for? This means that any choice that we could make when L is included, this is something that we could also do when L is not included. Because the possible choices are the ones in UT or in UT prime respectively. And in UT we only have more choices than in UT prime. And how do we prove this? We prove this via a very simple induction. Namely, what do we start from? Initially, what are our unmatched vertices, or unmatched offline vertices? Well, in the graph G, it's all of L. In G take away L, it is all of L except for small l. And what we now show is that UT is a superset of UT prime for all t. So the base case is t equals 0. This is just by definition. Well, this U0 will be a superset of U0 prime. Now let's turn to the 11th iteration. So in the tth iteration, what is it that is happening? We match the newly arriving vertex R to the smallest index neighbor in UT-1 or UT-1 prime respectively. Because these are exactly the unmatched neighbors, and out of these we'll take the one with the smallest index. Now what is it that can happen? We'll now have to do a case distinction. What does the algorithm on G do? Case 1 is that G matches this R to some L prime in UT-1, take away UT-1 prime, or not at all. What does this now mean? Well, in this first case, what we'll have is that UT will become UT-1 take away L prime. And UT prime, well, this can only be a subset of UT-1 prime. So in this case we'll see, okay, certainly UT will be a superset of UT prime. In this case here, we'll have that UT is equal to UT-1 and UT prime is certainly a subset of UT-1 prime, and so also here we're getting that UT is a superset of UT prime, and this is always using the induction hypothesis that of course this here is a superset of this, and also this is a superset of this, and what we're removing here even this thing here is a superset of this, just because it is outside the intersection. Now there's the second case that G matches R to some L prime in ut minus 1 prime. What do we get now? Now we get that ut will be equal to ut minus 1 take away L prime. And what about ut prime? Well, what now has to happen is that on G prime, R has to be matched the same way. So here, this part, this is actually important. And where was this coming from? This was coming from the fact that R is also matched to L prime when we're considering the other execution, just because if L prime is the one with the smallest index in ut minus 1, it will certainly also be the one with the smallest index in ut minus 1 prime. And this concludes our induction proof. Good. So this is actually nothing super spectacular. What is crucial here is that we use the same indexing throughout the entire execution of the algorithm, regardless of whether vertex L is around or not. And this is why this argument is true. If we were changing the indexing throughout the sequence, throughout what we're doing, then this might not be entirely correct. Or maybe it is. That's something you might want to verify yourselves. Most certainly, for our case now, this is correct, because we do not change the indexing of the vertices over time. Good. Now, where are we? We actually want to show this theorem. We already have this lemma, which we will be now using when we're proving this theorem. And the question is, how do we want to prove this theorem? Well, the idea is to more or less, again, use the approach that we used for the greedy algorithm, using the alpha and the beta, so the alpha L and the beta R variables, which will now turn out to be random variables, but nonetheless, generally the same approach works. What you should keep in mind is the intuition of this bank account where we're putting money into, and then this allows us to later on pay the optimal offline solution. Let's see how we do this here in detail. The first thing that we do is we consider a different but equivalent way of generating the indexing. For each offline vertex, we draw some random variable YL from the uniform distribution on 0, 1. And then we order L by the increasing values of YL. And I should mention that these draws are independent and identically distributed. So now each of the cardinality of L factorial permutations are equally likely. Just because we have this independence and also the fact and also that they are identically distributed. Good. Now what we'll do is we'll use these YL to define these alpha L and beta R. Namely, what we do is the following. If L is matched to R, we'll set alpha L to G of Y L divided by F, and beta R to 1 minus G of YL divided by F. And here G will be a function mapping from 0, 1 to 0, 1, and F is just some number that is chosen appropriately. So both will be chosen appropriately later on. And if L is not matched, we'll set alpha L to 0, and if R is not matched, we'll set beta R to 0. So what's the idea so far? We draw these YL from the uniform distribution. A smaller L means that the respective offline vertex is earlier in the indexing, which means it is more likely to be matched. And a higher YL means that it is later in the indexing. And remember that we always match the vertices which are early in the indexing first. Good. And now we define the alpha L and beta R, and we define them based on the YL. And so the way you should again think about this is money that we're putting into our bank account. If vertices are not matched, they just get a 0 value of alpha L and beta R because they're not contributing anything to our solution. Now, if L is matched to R, so if we have the matching between L and R, then what do? We now say alpha L will be something, beta R will be something that is greater than 0. The sum will be exactly 1 over f, so we put 1 over f units of money into our bank account. But we don't split this up evenly in general, but we split this up depending on the YL value. Because, or that's at least the intuition that I have, that if the YL value is smaller, this respective offline vertex is somehow get a smaller index, so it is to some extent more likely to be matched. Whereas if it is higher, then it is less likely to be matched. And this is something that we're now reflecting in this definition of how we split up the money. So maybe the way we split up the money is, how much are we surprised by the fact that this match now takes place? Good. First thing that we should do is we should observe that this actually generalizes the way we were analyzing the greedy algorithm before. Namely, if we set g of y to always be a half and f to also be a half, then we get the analysis that we had before for the greedy algorithm. Why that? Because this would now be a half divided by a half. This would also be a half divided by a half. So we would set both of them to 1 or to 0 if they are not matched. And then this is exactly what we were doing before. But what is now our hope? Our hope is that we can actually choose a smarter function g, which makes it actually possible to, well, put fewer units of money into our bank account. And what do we do? Well, the first thing that we should observe is that regardless of our function g, we can always use this to bound the value that our algorithm achieves. Namely, why is this? For any edge that we have in our matching, we'll have that alpha L plus beta R is exactly 1 over f. And so this means that if we now take the sum over L in L, alpha L plus the sum of all R in R, beta R, what we'll get is exactly 1 over f times the cardinality of alg. One thing that we should be aware of is that, well, these YLs, those are random variables, and this also makes the alpha L's and beta R's random variables. So we can also take the expectation of this here. This equation there, of course, holds regardless of these random outcomes. So we can also write this in terms of the expectation, of course. And capital F, this won't be a random variable. So we can move it outside the expectation. Now, what is the second part that we'll do? We will choose G and F so that the following is ensured, that for all edges we have the following, that the expectation of alpha L plus the expectation of beta R is at least 1. This, I hope, feels familiar because earlier we showed that exactly this inequality holds, but without the expectation, because there alpha L and beta R were no random variables. Let's see why this is actually all we need. How do the things combine from here on? Well, then we can write the cardinality of the offline optimal solution as take the sum over all edges in the optimal offline solution. What's the expectation of alpha L plus the expectation of beta R? That's just using this inequality here. Good. Now this is clearly upper bounded by taking the sum over all L, expectation of alpha L plus the sum of all R, expectation of beta R. Why is this? Because every L and every R appears at most once inside this sum, because we have a matching. Now we can use linearity of expectation. And now we can combine it with this here. So what we're then getting is that this is exactly 1 over f times the expectation of the cardinality of alg. So overall, this now means, if we read this from right to left, that the expectation of the cardinality of alg is at least f times the cardinality of opt, meaning that we are f competitive. So all we actually have to do is we only have to choose g and f so that this inequality is fulfilled. And what we'll do is we'll verify that for one particular choice of g, we get this for f being 1 minus 1 over e. Namely, what we'll do is we'll define g of y to be e to the power of y minus 1, and we'll set f to 1 minus 1 over e. So the important thing is, so far the definitions of g and f didn't actually matter at all, as long as we are able to verify that this inequality holds for our choices of g and f, we get that this algorithm is f competitive. And as I was saying before, in our analysis of the greedy algorithm, we were setting g to be constant a half, f to be always a half. There we verified this inequality even without any expectations. Now we are doing this with the expectations and with these smarter choices of g and f. You could also consider other functions, g, but then the value of f for which you could prove this would only be worse. By the way, this g actually has nothing to do with the algorithm. This is just a tool for our analysis. Cool. So how can we understand what is happening here? How can we understand these expectations? Recall that we are always putting money into our bank account. Namely, we're always putting 1 over f units of money into our bank account for every match that we make. But interestingly enough, this will now be a random variable. So the eventual balance of our bank account after having put in this money will be a random variable. What this is now requiring from us, these calculations, is that in expectation there's enough money in the bank account so that we can pay for the optimal offline solution. Sometimes maybe it's not enough money, maybe sometimes it is enough or more than enough money to pay for the optimal offline solution. That's cool, as long as in expectation the money is just enough to pay for the optimal offline solution. Good. So All we now have to verify is that with this choice of G and F, this inequality is fulfilled. So let's call this inequality star, and all we now have to do is we'll have to verify that this star holds. And how do we do this? Well, what we'll do is we'll consider a fixed edge L, R, and E, and we want to show that the expectation of alpha L plus the expectation of beta R is at least 1. And what we'll also do is we'll keep all YL prime fixed for L prime which are not equal to L. So what does this mean? The way I think about this is that we have our offline vertices L, our online vertices R, and now what happens is that we get these YL values for all of them here on the left hand side, and let's now draw it like this, that we say, okay, we have a value of 0 up here and a value of 1 down here. And now we have this one vertex L, which we don't yet know where it lands here inside this interval. This has one edge to our online vertex R, and now there might be other edges. Depending on now where this YL lands, we get a different value for alpha L and for beta R. So maybe this vertex, for example, never gets matched to R because this is what it looks like here. We've now fixed the other vertices, and maybe this has now got some YL prime, which is super tiny, so then it will always happen that R will use this edge here. Or it might happen that this L is super likely to be matched. This only then depends on YL. This is the only randomness that is left. There's the YL primes, those we fixed. And what we'll now do is we will consider the algorithm on G take away L. So let's get rid of this L entirely, and let's now see what happens to R. Well, maybe R gets matched somehow. In this case, I think it would get matched here, but maybe it does not get matched. And if R gets matched in the execution on G take away L, to some L prime, which will of course not be equal to L because there is no L in the execution now, we define the critical y to be the y of this L prime it is now matched to. So in my picture here, I guess this might be my L prime. And otherwise, we'll set yc to be 1. The critical y will set to 1. And what we now show is the following. That the expectation, taken only over yl, because the other yl prime we kept fixed, is the expectation of alpha L is at least 1 over f times the e to the power of yc minus 1 minus e to the negative 1. And the expectation of beta r is at least 1 over f times 1 minus e to the power of the critical c minus 1. Good. Where is this coming from? Maybe before we see where this is coming from, let's first see what this implies. This implies that the expectation of alpha L plus the expectation of beta R is at least 1 over f times, and now this is 1 minus 1 over e. So for f being exactly equal to 1 minus 1 over e, this will be 1, and this means we are done. Good. So where do these inequalities come from? Let's talk about this first part here. What about the expectation of alpha L? What was the expectation of alpha L? What was alpha L? Alpha L was g over yl divided by f if L gets matched and 0 otherwise. And what do we know about when does L get matched? Well, let's see again, what do we know in terms of the yc? How did we define those? yc was the critical y. This was where R gets matched in the execution on the graph if we remove L. So what is then the y value of the L prime it is matched to? Now what happens if yl, so the vertex that we're now introducing again, what if this yl is smaller than this yc? Well then, here in this step it would happen that R would instead prefer this L instead of the L prime. So this would mean that in this picture L is somewhere up here, gets a smaller y value. Or it might happen that L is already matched at the time when R arrives. But this is also good, because what we now have is that L always gets matched when YL is smaller than this critical Y. Just because at the latest R will then prefer L over this L prime that we use to define YC. So this means that alpha L will be at least, how much? It will be at least G of YL over F if YL is less than YC, and otherwise it will of course be at least 0, because this will never be negative. And therefore, what's the expectation of alpha L? Well, this is exactly the integral from 0 to YC. We're taking here the expectation over YL. G of Y divided by F dy. We now just draw this YL, and if it falls below YC, then we're getting this much, otherwise we're not getting anything. So this is something that we can write down like this. And with our definition of the function g, this would now be the integral of this function would be e to the y minus 1. And so if you now see what this integral will evaluate to, this is e to the yc minus 1 minus e to the negative 1. And this is exactly the first thing that we claimed regarding the alphas. Now for the betas, we'll have to do something similar. What do we know about the betas? Well, we still have the case that yc can be equal to 1. Did we even mention this explicitly? That yes, here we said that yc can be equal to 1 if r does not get matched on this execution at all. And then how big is this? Then here yc is 1, this will be 0, so this e to the 0 will be 1, so we're not asking for anything. So then we'll have this here trivially. Now what happens if this yc is smaller than 1? Now what was happening here? We were now talking about this vertex R, and how does this vertex R get matched in the execution on G take away L if L prime, if L is not present. And then we say it gets matched to L prime. Now what happens if we now add L again? What happens to R? How is R now being matched? Well, the amazing thing is we now know by our lemma that we proved much earlier that R will again be matched, because what we know is that this L prime will still be free to be matched. This is the lemma that we showed much earlier. Even on G, when R arrives, L prime is still free to be matched. And what does this mean? This means that R will be matched to some L double prime with Y L double prime being no larger than YC. And this means that beta R will be equal to 1 over F times 1 minus E, or let's first write this in terms of the G function, G of Y L double prime this is now at least 1 over F times 1 minus G of the critical Y. And this is exactly 1 over F times 1 minus e to the power of the critical Y minus 1. And so this also means that if we're now taking the expectation over YL, by the way, the value of YL doesn't matter at all for this bound, because we always get this 1 minus e to the power of the critical Y minus 1. Good. So, overall, let's once again summarize what we have. We have that the expectation taken over YL of alpha L plus the expectation taken over YL of beta R, this will be at least 1 over F times 1 minus 1 over E. This will be 1. This holds for arbitrary, so now this is only taking the expectation over YL, but if we now take the expectation over everything else, this will surely be true because these inequalities hold regardless of how we fixed these other YL prime. Good. To me, this proof is still a little mysterious, namely, I don't have a really good intuition about what is happening here. Nonetheless, I think it is not super difficult to at least get some understanding. What's the general proof idea? We take this one edge between one offline vertex and one online vertex. And what is it that we're asking? We're asking what will be the YL and the beta R values be like? Now what we do is we consider what happens when we remove this L altogether. And then this vertex R maybe gets matched somewhere, maybe it doesn't. And this tells us now something about what values YL has to take. If YL is taking a very small value, then it is of course likely to be matched, and we're getting into this case, so YL will have something in its part of the bank account. But this somehow is determined how much it is getting into its bank account in expectation is somehow determined, and how important is it? How important is this L? Is it that it can easily be replaced by everything else? So only when the YL gets really small, then it is being matched at all. This means that in expectation it will get only very little in its bank account. Or maybe it turns out that without L, R isn't matched at all, then it will get quite a lot in its bank account, or in its part of the bank account. And then we'll do the same thing for R. What happens when L is not around? Well, then it can happen that R is not matched at all, which means that R will always be matched to, or then, well, we don't really care about what happens to R. If R is being matched to something really good, meaning that it is very early in our order, something that is actually has a very small index in this ranking, then what we'll see is that even when we're now including L, this can only improve the situation for R. It can never worsen the situation if we include L. This is exactly the lemma that we proved much earlier, that when we remove L, this can only reduce the options that R has for matching. It can never add any options that were not before, that did not exist before. And what this function g is now doing is it is balancing off all these bank accounts carefully. You could, in principle, as I was saying earlier, do exactly these calculations also with other values of g, with other g functions. But what will happen is that you will get to this point, and then where we have this 1 over f times 1 minus 1 over e, or then this will not be 1 minus 1 over e, of course, and this then will depend on the yc. Here, this is carefully chosen such that exactly here and here the yc, here and here the yc just falls out of this if we just add the two inequalities. If we did not do this, then this wouldn't fall out and we would have to bound it somehow, and we would get a worse bound, but nonetheless this is possible. And as a matter of fact, it is possible to also show that we cannot do better than this, meaning on the one hand, well, this algorithm is not better than 1 minus 1 over e competitive, but also there is a very strong impossibility result, meaning that no randomized algorithm can be better than 1 minus 1 over e competitive, regardless of what it is doing. So, to some extent, this is the optimal algorithm, but optimal, of course, only in the sense of competitive analysis. Maybe if you had prior knowledge, you could do something a lot smarter. And this is exactly what we will be talking about next time, and also then the following weeks. How can we capture some prior knowledge? What can we do if we go beyond this worst case analysis that we were doing in the context of competitive analysis? This is it for now, for today. Please let me know if you have any questions, and hope to see you next time. Stay safe in the meantime. Bye.